Stars have this sort of reputation for going out with a bang, after millions, if not billions of years of providing light and heat to the planets that surround them, and perhaps even guiding some nighttime sailors out at sea. They explode and then sort of fizzle out, right? Well, some do, but they're a topic for the next video. In this, the penultimate episode in this Stellar Evolution series, we're going to talk about how stars like the Sun will end their time. This is how the Sun will die. Now, before I go any further in this video, I would highly recommend that if you haven't seen the previous video, that you go and watch that. I'm going to be building on some concepts that I talked about quite extensively in that video, and it seems redundant to explain them again. It'll be in the top right hand corner. Since you're still here, let's fast forward about 4.5 billion years into the future. Last time we talked about the Sun fusing hydrogen into helium in its core, but eventually that hydrogen is going to run out. This is the point we're fast forwarding to. All that's left in the core is helium, but this helium core won't be fusing. It's not hot enough to do that yet, but it is all about the same temperature. We call this isothermal. At this point, the Sun has no fusion going on inside it, so it starts to contract down. All the heat that's in it gets compressed into a smaller area and it heats up, increasing its temperature. It also gets brighter at this point. Now, since fusion isn't happening in the core, this helium core still has a bit of growing up to do. Around it, in a thick shell, hydrogen starts to fuse, creating more helium and increasing the mass of the core, until it reaches what we call the Schoenberg-Chandrasekhar limit, which you'll recall from last time is the maximum amount of non-fusing mass that can exist in the core of a star, before it collapses. When the core reaches this limit, it starts to contract down, releasing energy and causing the rest of the star to expand. The rest of the star actually cools down quite a bit because the heat is spread over more volume. Because it cools down, its colour becomes more red. This is called a red giant. While this shell burning and expansion to become a red giant is going on, the helium core is still contracting, until it's stopped in its tracks by something called electron degeneracy pressure. Electron degeneracy pressure is a consequence of everyone's favourite weird physics thing, quantum mechanics. In 1925, Wolfgang Pauli came up with the Pauli exclusion principle for electrons. Now, this states that no two electrons in the same trap can have identical values for their quantum numbers, which in normal person speak means two electrons cannot be physically in the same place. It's kind of like trying to cram everything into a suitcase. Eventually, there is nothing else is going to go in there no matter how hard you try. When the helium core reaches this point, it becomes what we call degenerate matter. It can no longer be compressed any further, but it can still get hotter, and its temperature starts to climb. The degenerate helium core gets hotter and hotter and hotter until it gets to about 100 million Kelvin. At this point, helium ignition takes place. But helium ignition isn't like the hydrogen ignition that we had when a protostar became a main sequence star. When helium ignition takes place, the degenerate matter is extremely temperature sensitive. In just a few hours, the core temperature increases by almost 80%, and the core luminosity increases by 10 billion times. This is enough to outshine a galaxy, but it never actually reaches the surface. This is called the Helium Flash, and it breaks electron degeneracy, allowing the core to expand a bit and to fuse helium, like it fused hydrogen on the main sequence, but through a process called the triple alpha process. The triple alpha process is a nuclear process not too dissimilar from the proton-proton chain and the CNO cycle we talked about in the previous video, which, again, if you haven't watched yet, I would suggest you go and watch. Again, top right hand corner. The triple alpha process differs from the proton-proton chain and the CNO cycle in one key aspect though. It includes endothermic reactions, reactions that take energy away from the star. These endothermic reactions take place in the first two stages of this three-stage process. The third stage outputs energy. In the first stage of the triple alpha process, two helium-4 nuclei, also known as alpha particles, are combined, giving us a beryllium-8. But this beryllium-8 atom is incredibly unstable. In 2 × 10⁻16 seconds, almost all of them have decayed back into helium, but some manage to pull in another helium-4 nucleus, creating an excited carbon-12. This carbon-12 is also unstable. The majority of it will decay back down to beryllium and helium, but some manage to de-excite successfully, releasing some 7.67 mega electron volts of energy. Now the first two stages did take in some energy, so the total output of this process is around 7.3 mega electron volts. Now this value is much lower than the value of energy output by the proton-proton chain and the CNO cycle. There is also much less hydrogen, so when you couple these two facts, this stage is not going to last anywhere near as long. It's also worth noting that some of the carbon-12 that's created in this process manages to drag in another helium-4 nucleus, creating oxygen-16, the stuff we breathe. Like with hydrogen burning, helium burning will not last forever. There's less helium, so it doesn't last as long. Eventually, the helium in the core is exhausted. While the helium was fusing, an isothermal core again built up inside the sun, this time made up of carbon and oxygen. Now, the sun is too small to ever get to the temperatures needed to fuse carbon. So this is the final isothermal core we're left with. But since it's run out of helium in the core and there's no fusion going on, it does start to contract again. This carbon and oxygen core becomes electron degenerate like the helium core did before it. Like when the helium core contracted, the carbon and oxygen's core contraction causes the rest of the star to expand, until the outer layers are rather weakly held by gravity. When the core becomes degenerate, it puts out a lot of radiative flux, and since these outer layers are held so loosely, it actually drives them off, expelling them into space and creating something called a planetary nebula, which incidentally has nothing to do with planets. When this nebula forms, it leaves behind the hot, dense carbon and oxygen core, which comes to be known as a white dwarf. A white dwarf is the end state of the sun. They're very hot, with temperatures ranging from 10,000 to 100,000 Kelvin. That's 10 to 100 times the temperature of the sun. And all that heat is packed into a very, very small area. White dwarfs are only about the same size as planet Earth. Because there's all this mass compressed into such a small area, 1 teaspoonful of white dwarf core material would weigh the same as a Boeing 747 aircraft. And although we count white dwarfs as a type of star, they have no fusion. They're just going to sit there for billions and billions of years, slowly cooling, until eventually they just fade away. Well, that ending was a little heavy, but that's how the sun will die. But not all stars will die like the sun, so make sure you subscribe and hit the bell icon so you don't miss my next video on how stars much larger than the sun, like the ever-threatening to explode Betelgeuse, will die. If you'd like to read more about this topic, then the blog post linked in the description has all the sources I used to create this video, so feel free to check that out. And while you're down there, please leave any comments, questions, criticisms or suggestions for future videos in the comment section below. Until next time, I've been Thomas, you've been watching Inversion Science, and I'll see you in the next video.